the board.
The homework.
Yeah, I'll take the homework from you if you have it, please. Thank you. If you need, like I said, if you need a little more time, that's cool.
Oh,
That's
thanks.
very nice.
I kid you not, I'm starving.
I'm also quite hungry.
I am too, so let's stop talking about it. I got this plum here, but I gotta talk.
A plum.
A plum.
Stone.
You've never eaten a plum?
No.
If this wasn't my only plum, I would give it to you, but
Is it like a peach?
No.
I probably
It's
ate.
it's like a big sweet cherry.
See, I probably ate the Google Translate
Okay.
version.
Huh? Okay.
The ones in my country.
Huh.
Something bad too.
Sketch that mofo!
Less than 2.
No.
You've already got it sketched. It's not
Overachiever.
terribly hard.
No.
So then, once you do that, let me keep Noah busy.
Yay.
Yay! I want you to find a few things here. Find the boundary. So find, first off, the interior. Find the boundary. I'm not gonna write find each time. The interior, the boundary, and any isolated points. We talked about all these things. I think we talked about those definitions.
Yeah.
Yeah, so that's a good place to start without going too much further. And then let me see, I know I have a new assignment in here, I better find it. Oh yeah, here it is. Yes.
These might be much.
Shite pen. Does it help if I put like homework assignments up in world class too? Or does it not matter?
I would enjoy it.
It wouldn't hurt, right?
Like just
That would be
announce
helpful.
it or something, that'd be cool. I'm not gonna hate you if you don't.
You've got so many other reasons to hate me. I mean, like,
I mean, I've been with you for a little bit. I mean, you know. Spend some time with you.
most hated math professor.
This is my last class.
I'll take that title. So yeah, this is the next homework assignment. I don't think next Wednesday sounds like a good day because we don't meet on Monday. So let's make this due a week from next Monday, aka
Next Monday.
yes, next Monday. So let's see, Friday's the 1st.
It's the 11th.
11th, thank you. Duh. Make it good. You've already got all these answers, for Christ's sake. No, I'm not pushing on you. It's just like, do I have to put more up there for you to
Do
do?
you want to put accumulation points?
Sure. Sure. Let's add that. And accumulation points.
The real part was Yay.
Good news, you don't need the quadratic formula for any of this.
What the heck? I don't have enough sugar in my system yet.
I'm pretty caffeinated at the moment, I'm not gonna lie. Drunk a whole monster since the last hour, so anyways.
This is a plum looks
Oh,
Big
it's
cherry.
not a pit like a peach.
Got a little bit.
Yeah, it's called a stone.
Do they grow on trees?
Yes.
No, they grow underground.
Wrong, first of all. I don't know much, but I know.
You're going on her
facts.
list. She's got me at the top of the list. You're next.
Long list today, guys.
You pull out this like roll of paper. Scroll.
That guy in the hallway, he looked at me funny. He's on there. I don't know what his name is. He's on there though. Guy in the hallway.
Let me actually give you a couple on. So still gotta keep Noah going.
No, don't.
Stop. Okay.
No, I was doing the Wonka thing where he's like, the kid's like about to die. He's like, oh, stop. Don't go on. I care so deeply.
Oh my God, this is not germane to our stuff, but I play this game, DeFi Kingdoms. It's a crypto game. This morning I hatched an egg and I now possess the single rarest pet in all of the lands.
I wish I understood what that meant.
Yeah, I don't know.
Just know it made Dr. T very happy.
It made me so
Yeah.
happy, and like semi-famous in a small community of geeks,
That's the best kind of famous.
crypto gaming geeks. So, those are good geeks. That's hardcore geek. Intersection of several geek.
A bit more hardcore
Circles.
than me, I think.
It's what?
More hardcore than I am, I think.
Actually, I think so.
It's also like my single greatest investment.
Yeah.
How much money have you put into?
Make a guess.
I said that before I was eating.
Okay,
Pretty better though.
so it has to be more than a console's worth. A few thousand?
It's a good start.
Oh no.
No.
That's because you can do like it's like open disk, right?
So ask your question again, please.
So like inside of the circle, like with the radius of the two. I'm trying to sketch that, but I have no idea.
So what is it? So let's understand how to maybe think about this. So if I have z is x plus iy, right? And you can always kind of think in terms of rectangular stuff as well. Doesn't hurt, thinking of that idea. So what is the real part of z? X. So you can translate that into the set of all x and y such that the x coordinate is less than 2.
Everything over yonder.
Everything over yonder. Indeed.
Not just the circle.
Here's one.
It's all of the things.
Alright, now let me see what I got here. I don't know if any of these. Oh, this one might be painful. That
Ooh,
was good.
okay.
You should get that checked out.
Same.
That's a plus, believe it or not. Good.
C minus I.
Excellent one.
Equals C plus I. I think so. Go over.
And then do all these things for it as well. Hi. No, where do you get, so I'm curious, because Nathan was mentioning circles, where's the idea of circles coming from? I'm just curious.
We were working a lot with circles.
Yeah.
I think that's just the default we're
Okay, there's no circles in this.
Cool.
Yeah, that's it. I mean, in a way, it is a circle, but one of the points on the circle is at infinity. So theoretically,
Really big circle.
a really freaking big circle. And we'll see, that'll make sense a little later when we talk about the Riemann sphere.
The Riemann
Oh my
sphere.
goodness.
Oh my lord.
Super cool. Just take the whole plane and cinch it up into a little ball.
Because you know what I don't mess with? Riemann sums.
Well, good news. Until we get to integrals.
That Riemann guy really did a lot.
He got around.
He
He got around.
he got
What are you thinking? Oh, yeah, quite good. Damn. What the fuck? Okay, good.
Yeah.
yeah, nose cooking up there.
Alright, now what? Next.
Okay. Let me do this.
Why are you only writing on one side of the paper?
Cause I like to make notes, I like
Me
make,
neither.
like what I wanna talk about, and then when I go through it again, I make side notes.
Okay.
It's not always the case, you see?
Okay. I see.
I'm not being wasteful. Deliberately so, anyway.
Question.
Yes,
Mm-hmm.
yes, ma'am.
Theoretically,
Oh boy.
I know what interior and accumulation points are. Isolated points, blank.
Isolated point, point is isolated if I can draw a circle around it that doesn't intersect any other parts of the set itself, so.
like, for that first one, anything where x is greater than 2?
Well, so an isolated point needs to be in the set as well. So like, if we did this and we unioned it with like, 3 plus I, and I tossed that in, and then, well here, let's just make sure we all got the region here first, right? So it's 1, 2, cannot get to 2, but I can get as close to 2 as I want. So this is the region we're talking about. It's like that whole section of the plane, because any number you pick here, its real component is less than 2. So we're just looking for all of those. But if I tossed in this 3 plus I, that now becomes an isolated point because I can find a disk around it that doesn't intersect any other parts of the set. There's like distance between you and everything else. Like, let's go back really quick to this example I had the other day, where Z was just the 1 over n's. And here, let's see, I think I got shed for writing Z plus from someone, so let's put natural numbers.
That was me.
It was, I know quite full well who it is. We had these points here, and they were accumulating at 0, right? So they were getting closer, and then 0's not in the set, but it is a place where they're bunching up. They're bunching up there. All the points, every point in the set is isolated. Every point in there. Because no matter how close down you get, so let's get down here to 1 over a Google. Now I'm down, that's like freaking small. Your calculator will say 0 if you enter that, probably. So this number, this is still, right, and then, but there's 1 to the left of it, and it's 1 over Google, 1 over Google plus 1 down there. So I just add 1, and I move to the next number to the left, and over here is 1 over Google to the 100th minus 1. And, this is deep down in there, but it all kind of looks the same. Every single one of these points I can just make a disk around that doesn't touch any other point in the set. So every single point here, these are all isolated. They are accumulated. So an accumulation point is not isolated because stuff gets infinitely close to it. But everything in here is definitely, you just zoom in far enough, they look a mile apart. So these are all isolated. None of the points in this original set, so if I take that back out, let's go to the original problem. None of these points are isolated because you draw any size disk you want. Oh, it's like, oh, I'm gonna draw a really tiny one. Doesn't matter. There's still stuff from this set inside that disk, no matter what.
Oh,
So
okay.
nothing is isolated.
I understand.
So the isolated point has to be something outside, technically outside of this.
Yeah, it's just kind of a lone point. Yeah.
And the accumulation point would be 2, because everything is like going as close to 2 as possible.
Yes, in fact, the accumulation points are all the points along this
yeah.
line.
So where x equals 2.
Yeah, x equals to that.
Exactly. So so let's write this
But
up.
wouldn't they also be every point in the set? Because
Yes, exactly. Yeah, so it's actually
Less than equal to 2?
less than or equal to 2. Yeah, perfect. Yeah, exactly. Because every point in here is definitely an accumulation point because things are clustering up around it. Things are clustering up around this line from the left side. So let's just say here. So our let's give this a name. So G. I'm going to use G prime because that's like not an atypical way to say accumulation points of G. But here, that's gonna equal, the notation for accumulation points is like, I've seen so many, but I've seen that one a couple of times, is just the set of all Z and C such that the real part of Z is less than or equal to 2. The interior, let's go to the very first one. What is the interior here?
Zero.
0 is part of the interior. Why?
Because there's no Y value.
No, I don't think I think we need to think about this a little bit. I think Grace is like waving me down.
And then it was just like past the.
So yeah, so can you say it more precisely?
More,
Mathy.
it's like everything that is less than 2.
It's the original set, right? So an interior point, I'm an interior point if you can draw if there exists a disk around me that's completely inside the set. So I am an interior point if I'm surrounded by parts of the set. If everywhere I look in a little short radius, some short radius, all I see is set around me.
Yeah, okay.
Yeah, so this is the accumulation points. The interior is sometimes denoted with a little O for open. And this is just the original set. Its interior points are every point in the original set.
So
Yeah.
technically,
Yes?
for this set at least, interior points are the complete opposite to isolated points.
Yeah. Well,
And this.
accumulation point is probably more the opposite
Well,
of isolated.
that
Yeah,
makes
yeah.
sense.
But an
But-
accumulation point doesn't have to be in a set. Isolated
Oh,
point-
that's true. Really good. Okay, so excellent. Yes, absolutely. So accumulation points don't have to be in the set as this is, but yeah. So I guess in terms of things in the set, that's probably pretty good. Yeah. Just think you're surrounded by the set though. There's like no space where you're outside the set. So that's interior, it's just the original set. What about the boundary? What does it mean to be a boundary point? What's the definition of boundary?
B is a boundary point that is both in and out of the set, and is a closed disk.
How can the point itself be both in and out of the set?
A dot at the very edge and then a circle around so that half the circle is in, half the circle is out, I think, I don't know.
If
This is
every-
getting there. We're getting there. Let's be more precise.
If every open disk centered at B contains a point in G and also a point that is not in G.
Boom.
So like what she said.
It's.
but
I was just trying to get you to be more precise with the language.
you just wouldn't.
so- So is this point here?
No.
No, because there's a neighborhood around it that's it's an interior point. You can't be an interior point and a boundary point.
I sure hope not.
This is a boundary point because no matter how tiny the circle is around it, it spills out and it spills in. It's all about those circles around the point. Start thinking that way. That's topology. Neighborhoods around points. Yes?
And okay, so this point, bless
Bless
you,
you.
the point that we're building it around, does that point have to be in the set?
Wait, where we're talking about, what was
So
Hey.
you have a,
boundary
on
point?
the
Boundary does not have to be in the set.
okay, so it's okay that it's on 2, even though 2 is not?
Exactly. They're kind of like accumulation points in some ways.
Okay.
In fact, every accumulation point would also be a boundary point in some ways. I'm gonna take that back.
Every boundary point would also be an accumulation.
No, I said absolutely.
Definitely a boundary point is an accumulation point. So let's get some notation. If I use this symbol, this del symbol, use that for like partial derivatives, but it's also used in topology to indicate the boundary of something. And here, what is the official, how do I write it in that set notation? It's the set of all Z and C such that what?
Original Z equals 2.
Solid. Yep.
Beautiful.
Beautiful indeed. And just think the x coordinate is 2, right? You can make these translations. This is what this is all about, getting used to like thinking this way. So the boundary of Z, G is just this thing. And let's see what else we got there. Any isolated points? No. We already kind of talked about that. There's no isolated points here. Very good. Most excellent. Let me toss in a new definition because this set has a very nice property. It is an open set. So let's get a couple definitions up here that we haven't talked about. A set G, and we'll just stick to the complexes, is open if, and this is just one characterization, G is equal to its interior. If it's the same, if you find the interior of the set and it's actually just the set, that's an open set. Open sets are soft on the edges. There's this like dotted fuzziness along some edge. And that edge might not be quite visible, it might be way out at some other place, but that's a good way to think of it. They're soft sets. A set G is closed if it contains its boundary, or if it contains all its accumulation points. So let's write out a couple things here. So set G is closed. Let's go with this one. If G contains, let's just go with accumulation points, all its accumulation points. Let's just put one more up here. Define the closure of G. So this notation with that bar, this is the closure of G. The closure of G equals the original set union its accumulation points. So this is add in, so union in the accumulation points. All of them. Let's go back to that set here. Let's call this set H, and it was this 1 over n set. This guy here, we had 1, half, third, quarter, dot, 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 dot. What is the closure of H? So you think to yourself, okay, does it have any accumulation points? Say that again, sorry.
Does it have one accumulation point?
It has 1 accumulation point. What is that point? 0, right? So think, accumulation points are where things are getting infinitely bunched up. It's just clustering. Sometimes they're called cluster points. So the H, we just take the original set and we union in 0. So I'm just going to toss 0 in. Oh, you okay? Ouch. Keeps you awake. Oh, is that what it is? Yeah,
When
caffeine
you
and
like
pain.
napping before this class though?
Huh?
When you napping?
No, I was actually in the math office before this class trying to finish the homework for this class.
Oh,
Like I said, that was a lot less of sitting nap.
Yeah, usually I am asleep between our first class and this one though.
okay. Good to know.
Which sounds like the sleepiest possible way to attend class. You're probably still like hazy.
I do set my alarm for 5 minutes before I'm supposed to be here.
You are a fast waker upper.
I just put my shoes on. That's literally all I do.
Beautiful. Beautiful. All right, any questions on this? Let's take a look at this one. Take a moment and just, what is this asking us to do? What point? Read this in terms of the language of distance. Remember that the distance from Z to Z1 is this. Use that language and that interpretation. Just take a moment on this one. I'll find something else to know what it is.
Yeah, I can bring like a book or something.
No, you're not. No, I'll bring a book. I'll bring a book for you.
Okay. That's fair.
That's so funny.
Shit. Let's see. What can I get to do? So I'm teaching this Inside Out class to folks who are incarcerated, and like there's a couple of them that are just like terrified. No matter how slow I go, no matter how like not mathy the things we're doing are, they're terrified because it's math class. And then I got this whole group of guys down at Territorial, down by Pueblo, I guess. And those dudes are so stoked about this class. Like, I cannot keep them busy. I keep giving them projects, and they're like, I got it done in overnight, and like submitting me beautiful Excel sheets. And I've got to like run a second class for them to keep those guys busy.
I love that.
They do too.
Great.
They're like, God, can we start? We finished. They're like, can we go ahead and start the next section? And I'm like, yeah. And they'd started the class before the class started. They were learning stuff that wasn't in the class. And they came in and they're, we have some questions on this chapter 9 stuff. And I was like, guys, we're not doing chapter 9.
What about chapter 1?
Yeah, we're gonna start chapter 1. They're amazing. They're really cool.
That's hilarious.
Yeah, it's exciting. It's exciting and also stressful for the folks who feel the opposite. Oh God, let's see, what can I do for you now? Good Lord. Oh, hey, why don't you check out problem 118?
Can I,
Yes.
thank you.
Just Noah. I'm pretty sure it's not about just Noah. That's fine.
It's kind of a cool problem, so. Grace, your pants are awesome.
Thank you.
So cool.
My friend's mom bought it for me. Literally half of my wardrobe is just my friend's mom giving me shit.
Yeah, I need a friend.
I think I want, and backpacks from your dad, so like, yeah. Man, I think I want a pair of those.
Anytime my dad has a warehouse sale, I'll put you on the list, so, cause they're like 50% off for shit.
Me
The
too.
rest of us.
I mean,
Come on now.
What are we doing?
118 you said?
Noah's doing 180.
Noah's doing 118.
We're doing
You're
that.
doing this, and then when you're done, you're doing 118.
While Noah does chapter 7.
Then one day.
I have some questions about chapter 9 as well.
Damn you, Noah.
I do not doubt that.
The
Nah.
two Noahs I know are such know-it-alls.
You mean the 2 that sit right next to us? And
Yes.
Uh-huh.
There's more. There's so many more of us.
It's just
Look, I don't care. You do it enough.
From the board game club, there's 3.
But he's not arrogant in
No,
any
he's
way.
not.
He's just like a lover of knowledge, you know?
He's a
Makes it even
sweetheart.
more
Yeah.
annoying.
He just knows
There's
so
no
much.
arrogance.
Z is a complex number.
Correct.
Okay.
That's a good assumption from here on out. Always.
It's possible you're not.
Like if you're asking yourself, I wonder if complex numbers have something to do with this problem.
Probably.
Probably, yeah.
Yeah.
Every single problem, all of the problems. Can somebody read this to me? Not Noah. He's working on a different problem. Can somebody read this to me like in an intuitive way? How would you, so I'm a student coming to you for tutoring. What are they asking here? Help me put this into just plain English.
It's just saying that the distance between z minus I and z plus I are the same.
Or the distance between z and I.
Yeah.
Right.
Yeah.
And the distance between z and what point? What am I minusing here? Negative I. So I would rewrite this as the distance interpretation. And that makes that a whole lot easier to think about. So it's saying I want to find all the points in the complex plane, z, who are the same distance from I. So let's write this up here so that it's there. Distance from I equals the distance from minus I. So we plot those out. Give me a point in the set. Low-hanging fruit. I mean, this shit's rotting on the ground. We'll get drunk if we eat it. It's that fermented.
Oh, say yes.
A little early.
Speak for yourself.
So tell us more about these naps, Sydney.
It would
No, I
be,
swear.
it would be the
Sorry.
earliest to drink a beer this semester.
Swear to God.
It's college.
No, I have a brew class, so.
Oh,
But yeah.
I have a beer class.
Yeah.
It's independent study.
I'm gonna get certified.
Oh, are you doing that?
As you should.
Thingy?
Distillery thing.
Yeah.
That's cool.
It's
So,
cool.
yeah.
Give me one
0.
freaking point. Thank you. Right in the middle, right? That's in the set.
Beautiful.
Could I have another?
Wouldn't it just be anything on the?
Y-axis line in I and I.
Those naps are paying off. Yes!
Bro, I'm telling you.
It's all of these. Because the distance to any of those points, z, is the same.
Beautiful.
It's just, say it in complex analysis, in terms of the complex plane, what geographic feature is it? It equals the what? The real axis, fuck yeah.
God damn it, I love you.
Yep, good stuff. Okay, so let's go back to the questions I asked you about the other set, and let's answer them about this set. So please find, let's see, what was the order? Accumulation points?
Interior boundary isolated accumulation.
Okay, so yeah, we'll call this K. So find the interior of K, the boundary of K, and this, I think I used that notation. This is the boundary of K, and then, what was, Sydney, help me out.
Isolated and accumulation.
Okay, thank you. And then find the closure of K, which is K union its accumulation points. Getting anywhere with that guy?
Yeah.
Cool, cool. Are you just doing the next homework assignment now?
No, I'm still on 1.8. I don't.
Oh, okay, okay.
I haven't started. Yeah, not that far.
You said the interior was where it was just surrounded by more of the set.
It's like thick there, right? It's like, can't move any direction and leave the set. Can't move in any very small direction. sufficiently small. Consultation. Let me know. Everybody know I put the videos up? Everybody knows that they go up on YouTube? Okay, cool.
I get your notifications.
Awesome. You think you got it, Lou? Awesome. So, yeah, is that your application? Yeah, cool. I like that.
It makes sense in my brain.
Yeah, no, it's, so I'm not quite sure I understand that, what that means.
I don't know, it was kind of cracky and strong, there's not really a meaning, it's just a line.
So, but yes, and I know what you're you're right, but this set doesn't really describe anything, it's just saying, you would need to like either set that equal to something, you see what I'm saying? But we have another function that'll make this easier, the imaginary part. What does the imaginary part need to be on that line?
So you also said
So, yeah, so I would say I am a Z,
Yeah, basically.
zero, and then that describes it. Cool, I like that you're trying to use that notation, I think that's what you're trying to say.
Yeah.
Yeah.
I was just like,
Cool.
saying just the line.
Yes, yes, so then this one, right, this one needs a little, yeah, yeah.
I mean, I guess we just need some of the actual
I
stuff.
thought it was just every point.
You don't need all of them.
Yeah.
Every point,
It's not-
all
you
the
don't have to do
points?
that exactly every time.
So are we looking
It
at
has to
boundary,
be
is that what we're
Just
looking at?
some outside and
Um,
some inside,
So, let me
You
see,
would just have the one point
so let's take a point out here.
for the axis for
Is there a neighborhood I can draw around that doesn't touch the set and touches the set at the same time? So boundary point means that,
Okay.
well, where's it touching
Not
in here?
outside
See,
of
I
the
can't figure that out.
Because
Just in the center?
So where's, yeah, so is this point on the boundary, I guess is what I'm asking.
Yeah, but I'm on the back.
That's what we're trying to get at. So this point is not on the boundary, because I can make a disc around it,
Or you can.
and it's completely outside the set.
That's also valid.
So that point's not a boundary point. What if I get really close?
Yeah.
Is that a boundary point? Not because I'm making a disc, right? What if I'm on the line? That is a
You
boundary
should.
point.
Yeah, no, you
Any
really
disc I
should.
make has points in and out of the set.
Yeah,
That's
they
my question.
have
So
to.
that's
We
the
are
already on the set.
wholly
Yes.
it.
Okay.
That's what we are.
Or I was trying to figure which set.
Well, the set is that just the real axis
Okay.
set. Yeah, yeah.
Well, you just wrote down, how do you know that's the set?
We just talked about this.
So, so when I was talking about the distance interpretation.
Oh, okay, okay.
Does that make sense? Yeah, yeah, okay, cool, gotcha. Oh, it's, you don't need
Like
to,
it's
it's all good.
zero where it's like.
Is it?
I thought it was a completely different, like,
Oh, gosh, okay, well, that would be
The two
really,
boundaries,
yeah, that's a
everything
hard
goes up
problem.
to two, but it doesn't
yeah,
actually
that
fit
is
to
part
two.
of the whole
Wouldn't that
process.
be like,
Got it, cool.
No,
Thank you.
for the
Wow.
information point.
because
Yeah, because for the information point on the last one was like
What we doing back here?
everything less than.
so it would be.
But that's good, that's like all things.
Okay, cool, so you're
That
saying,
this is just on a single line.
what does this set describe?
Clustered on that.
I see, I like the notation, it's good notation.
So is it not just the
But
same answer as interior?
What are you saying about the real part of
So
this?
then it's
We'll just go with.
Right, cause like right now, that just says,
So there's no.
the set of all Z and C such that
it's
the real
everything's
part
the
of
same
Z,
answer except isolated.
and then there's, that's like the subject of a sentence, but there's
Yeah.
nothing else, do you see what I'm saying?
It's
Like it needs to be like an
possible.
equality or an inequality or something.
Oh, and then we also need the, what's that?
Oh,
The
this
unit
other thingy?
real axis
the closure
Yeah.
of K has to be RI.
So, yeah, this is what I was talking, yes, yeah, perfect. So what you would say there is the imaginary part is always zero. So you say I am, capital I, lowercase m, of z equals zero. And then that also describes this exact same set. Does that make sense?
With the.
No, I would not, yeah, it would
So
be,
the boundary is already the set.
No,
it would be
It's with the
possible to do
accumulation
that.
points.
No, I don't even think it's actually
Right?
Like
possible
it
to do that.
contains all the
so it's the
But
set
if you were,
plus
yeah,
accumulation.
does that make sense?
Yes.
Awesome, good, good,
Okay,
good, good.
Right?
I don't know, this definition that I wrote down from the books was brown. I could be capping though, and I could have misread, so. Don't take anything I said seriously.
How much stuff is inside here?
everything.
All of the stuff.
Everything?
Wait, are we talking about the interior?
You're talking about the interior.
Oh, we did say everything.
Yeah, we did say
No,
everything
So
on
this
the
is
real.
in the
No,
interior?
like on
No.
the real axis.
No.
Where the
So like when
imaginary.
imaginary
Oh, okay,
equals
cool.
zero.
So you're saying like this point here is in the interior?
Yeah,
Yeah.
What does it mean to be in the interior?
in the set.
There's a big, like there's space around, like everything in every direction is also in the set, right? So I'm in the interior if I can make a little disc around me and that little disc is also in there. Thick, think thick for interiors.
So
Okay,
nothing.
so nothing.
Empty set.
Well,
nothing.
we were just on the other end of the spectrum.
You were just completely,
Okay.
and I knew you meant to say compliment. The compliment.
No,
of
absolutely.
everything. Absolutely.
Well, technically you got it right. Because you're like, imaginary is gonna be zero.
But no, that's the real axis.
You gonna be a lawyer, Lavina, instead of CS? So the boundary, where's the boundary? I'd say zero's on the boundary, yeah. The whole real axis.
Okay, that's the one.
The original set is really, it is its own boundary. Because any point that I pick in here, no matter how I make that disk, there's stuff in the set and stuff outside. In and out contains both. So the boundary of K is just K. And let's write that. So this was, folks were having a tough time getting the notation. So the boundary, we could also just say this, it's all the points where the imaginary part of Z is zero, right? Kill off the imaginary, and it's just the real stuff. No imaginary parts there. Or you could say it like we said it before, but this is like, this set is that set. They're the same thing. Are there any points here that are lonely like that? Are there any lonely points in this set?
No.
None. So isolated points, what do I write?
Empty.
Interior of K.
Technically speaking, he's
yes.
not wrong.
Correct, he is quite right, yes. He's being saucy. Accumulation points. Where's a point that no matter how small the circle is around it, and it doesn't have to be in the set, but no matter how small the circle is around it, it touches the set. So-
All over the x-axis.
Yeah, so definitely every point in the set is an accumulation point. Is anything outside of the set? Just make a tiny enough disk and it doesn't touch. That is, so no accumulation points except the original set. So K. What is the closure of K now?
It's just itself.
K, you take the accumulation points and you add them on, and you get the closure. But it turns out the accumulation points is K. So this is going to be K union the accumulation points, which is just good old K. Hey, here's a cool definition. The closure of a set is equal to itself. It's closed. K is closed. K is closed. And I did that K because I'm thinking like of a fancy kind of set called a compact set, which is also closed. Right? That's got other properties. And I'm thinking of the German word, yeah, compact. So K is closed, and yeah, K is closed because it's equal, K equals its closure. So that's another way to think about open sets. So here's a little fun thing about open and closed. And an easy mistake to make, I just want to make some notes. A set can be open and closed.
No.
Neither open nor closed. And those are the two. So the thing to think is, oh, this thing isn't open, so it must be closed. That is not true.
Of course it's not.
Of course it's not. What's an example of a set that's open and closed? So let's put an EG here.
Oh. We need open and closed, and neither open nor closed. That's
No, just this one first. Yes, yes. So
Okay.
this is or,
Oh, okay.
that's why, sorry, that wasn't
Okay.
clear. Yeah,
Great,
yeah.
great.
So think big or think very, very less than small.
It's pretty small.
What's the biggest set we can think of in the complex plane?
All of them.
The whole plane is actually both open and closed because no matter what point I pick, I can make a circle around it and that's all contained in there. So its interior is itself. And what is its boundary points? Well, its boundary points are also itself,
It doesn't have boundary points.
yeah, it doesn't have boundary points. So by nature, therefore, vacuously satisfied, that is closed.
So not having a boundary point makes it open or closed?
Yes.
He's lagging.
Yeah, it gets there, no, that's very convoluted. So let's see, why is this closed? Oh, because every point is an accumulation point. That's a better way to see it.
Oh, okay.
That's neat. Don't think boundary, that's like fucked up.
Okay,
But like think accumulation point. Every point is an accumulation point because no matter how small the neighborhood is around it, it intersects the set.
Beautiful.
So it contains all its accumulation points. Here's a tip, and this will help. This is a fun fact, incredibly deep fact. If G is closed, G complement everything not in G is open, and vice versa.
That's not
And actually, so let's do that. So G is closed if and only if G complement is open.
I like that.
Cool. What is the complement of the whole plane? So what is C complement?
It's not.
Yeah, it's not. Say something more massive.
It's empty.
Empty set, yeah. So the empty set is the complement of C. C is open, so the empty set is closed. C is closed, so the empty set is open. So there's only two sets that are both open and closed, and they are right there. C and the empty set. Everything or nothing. Those are the only sets that have both. Can you help me find a set? Can you construct now a set that is neither open nor closed in the complex plane? There's like infinitely many answers for this one. It's not just those two, right? That's a tricky thing. Build me a set. What if we start with an open set
Okay.
and then fuck it up?
Love
So let's start with this set. So that's open. What does that look like?
Everything less than one.
Yeah, so it's just the open unit ball centered at 0. Yes, Lavina, yeah, what you got?
Couldn't it be like we have two boundaries, one's like less than equal to or greater than equal to, and one's just less than?
Yeah, exactly. So I'm just gonna toss in a few boundaries. I think this is what you're getting at. I'm just gonna toss like 1 point on the boundary. Right? Or how, let's make an easier one to write. So now, look, I'm gonna add that point. So I'm gonna take this point and union in 1. So I've taken the open circle, added a single point. Now, and I ask you, is this set open? It's not, because this just screwed up openness. This set, every neighbor, that's actually a boundary point, right there. So I added part of the boundary. Boundaries are not part of the interior. So this is not in the interior. Why is this set not closed? So this is not open because one is not interior. Why is it not closed?
Can we describe that with accumulation points?
Yeah, what are the accumulation points for this?
Everything less than the boundary, I think.
True, but there's more. So everything inside the circle is absolutely an accumulation point. Is this an accumulation point? Yeah, because look, every ball around it contains points inside the set. Every punctured ball around this. Where are some other accumulation points, boundary points?
-1.
Oh, yeah, cool. Yeah. Is there there's like 2 more, 3 more? One more? Yeah, yeah.
Oh.
Oh, wait, we got them all?
No.
Good to go? No.
It's the entire circle.
The whole freaking boundary, the literal boundary. That's the closure of that set. So I'm just tossing in the rest of the edge. Everything on the edge is an accumulation point. Do we agree? I'm wishing I had my iPad and I can go back now. But here's where we had, because I'm looking at the faces and I see how they're going. So we had this set. Is this a boundary point right on the edge?
Yes.
Yeah, because every neighborhood spills in and out.
Yeah.
So that's on the boundary. So every point on the edge is a boundary point.
Uh-huh.
And when I toss those all in, I've closed off the set. So another way to think of this is G, closure, is G union its boundary points. Just make everything nice and solid.
Somehow that makes sense.
Oh, that's awesome. This is hard. This is conceptually new. It's very hard. Don't worry, we're going to be using this throughout the semester. And not in this way where you have to really worry about it. Just when you see the words, you're like, oh, that makes sense. I saw that back in the day, this day. All right. Any questions on that? Because I kind of want to move on a little bit to just one more thing that is on my agenda.
I mean, probably, but I don't know what those questions are.
Well, yeah, as they come up, let me know. One other thing we really are, this is something you definitely are going to have to be good at.
Oh boy.
Oh yeah.
That's a lot of questions.
Who's had Calc 3?
Yeah.
You don't need it. Do you remember parameterizing curves in there?
No.
Yeah.
We're going to do that and see.
I think I like that. I think I like that.
I
You
remember,
like
I need to see it to remember it.
Yeah.
Yeah,
Yeah.
I kind of remember it too.
I think that makes sense to me.
This is a fun challenge. I think. I was messing with it when I should have been doing something else this morning.
That sounds so familiar.
Yeah, doing math instead of doing
Yeah.
whatever else is actually on the table. Yeah.
I feel like that's how mathematicians are born.
I think that is true. That is true. So let's just talk about parameterized curves. This is way more important than the topology part. I want to give you a couple basic formulas. So first off, what is a parameterized curve? You can think of this as it's a collection of points, a locus of points in C, described by a function and I'm going to call this function R of T. You can call it whatever you want, which actually maps from some subset of the real line. So the input T, this is a real number. and it shoots out stuff into the complex plane. So what you can do is it's basically taking a subset of the real line. So like it's taking this G here, this is R, and it's just laying it down in the complex plane. So if this is R here, let's actually make it a nice closed segment like that. Let's say that's T naught and that's T1. Then I come up here and I've got this start that course, so here's R of T0. And then it kind of just does some stuff in here, and then it ends when I get to here. Here's R of T1. And I can think of this as a direction of travel from less to more. And so this thing will have an orientation as well. And so like here, if this is just an arbitrary point T, then up here somewhere I'll have R of T from that picture. So really just think of it as taking a line segment, stretching it, and laying it interestingly, or maybe not too interestingly, in the plane. I want to give you some tools. You're going to need these ad infinitum. Well, probably finitum. Because all is finite, alas, no matter how hard we try in math class. Everything ends. So, some very useful parameterizations. And I'm going to set these up for you so that it makes life really easy.
So you're saying we should highlight these in the notebook?
I would do that. I would get out your highlighters. Yeah, that pink, that'll be good.
Beautiful.
Yeah. So first off, for a line segment, incredibly useful, between Z naught and Z1, which are just 2 points in C. Draw a picture. So my real axis, my imaginary axis. Here is Z naught, and here's Z1. And I want to describe all the points on a line segment joining those two. So the parameterization for that is really what I'm doing is I'm taking a thing called all convex combinations of these 2 points. That you don't need to know that, but that's a fancy way to say what I'm about to do. So what we can do here is say that R of T equals, now I want to start at Z naught and I want to end at Z1. Actually, leave a little space in front of it. It's like fucking happens like every year. Like I know there's no other times to like do that.
No, absolutely not.
Never, there can't possibly, that can't happen really early or really late or on the weekends.
Nope.
Okay, cool. So, we're going to use T as our parameter, so T is the parameter. And I need to come up with a range of values for T here. The mode I'm going to give you here is going to be, I'm going to give you a simple route, and then I'm going to give you a fancier version of this. Because I think this will be a good place to make sense. We're going to let T just run from 0 to 1. I'm thinking direction, so I'm kind of thinking when I'm at T equals 0, I want to be here. When I'm at T equals 1, I kind of want to be here. So what I'm going to do is say, look, when T equals 0, I just want pure Z1, when T equals 0, I just want pure Z naught coming out. So I'm going to put T right here, and then when T equals 0, it kills that off and leaves this, but how much of this do I want? I want 1 minus T of those. So when T equals 0, I'm at Z naught. When T equals 1, I'm at Z1, and this is dead. So notice how at the extremes here, one of these two is killed off. This is a linear combination, so it's not shocking that I've got a line over here. This is the most fundamental thing we'll need to do. But I want to give you a different form of it, because sometimes you're not going to be able to just pick 0 and 1. So, or more generally, on T naught to T1, so let's say my parameter space is not necessarily the 0 to 1 interval, it's like 1 to 2 or 1 to 7 or something like that. So what we're going to do here is that R of t equals, and let's leave parentheses z naught plus parentheses z1. So when t is at t naught, I just want z0 to come out. So here I'm going to put maybe I can just, let's try this. Let's see if I put t1 minus t here. Then when I'm at t1, this is dead, and oh, yeah. And then over here, oh, shy.
Okay.
Sherbert. So I wanted to put, what I was gonna put, and this is what I was doing during the thing I should have been focusing on. So let's check this out. So when, oh,
So you just have to divide by
the difference.
Yeah.
Yeah. So we need to take this over t1 minus t naught, and then this over t1 minus t naught. So that we don't have a multiple. Check that out. So let me show you that this is legit. So R of t, yeah, that's what I was missing in my thought process earlier today too. So R at t naught is going to be this t1 minus t naught over that. That's just z naught. And this is dead because you've got t naught minus t naught. And then R at t1 is equal to, put in t1, this dies, and over here we just got z1. Yay, cool. Yeah, that's it. Keep that, like put a star when you're asked to parameterize stuff on your next assignment, and you will be. Good thing. We're gonna practice more of this. We're not gonna have a full enough time today, but I just wanna get you started. And then I got one more parameterization that's just absolutely vital. So that's the line segment one. On, let's do a circle of radius r centered at the point z0. So let me draw the picture of what I'm talking about. I've got this point in the plane z0, and I want to describe a circle around it of radius r. What, you think you got it? You think you know?
It looks extremely familiar.
I like this. Those naps are good.
It's like cars.
What do you think it is, Sydney? Let's see if we can draw it up. Man, you're getting me very excited about what's about to come out of your mouth there. Oh, no, let's not call it R. Yeah, no, fucking we'll call it R.
Okay.
Because I wanted to use R for the function name, but oh well. Let's just say C of t, sure. Circle, C, circle. That could be L of t. Equals. So first off, I'm going to take this circle of radius r here. What is the formula for the one centered at the origin? What is the formula for this circle using exponential notation? Yeah, the e to the I stuff.
Oh.
How do you describe this circle? Yeah, where's this live? I've made this point a couple of times trying to drive this home.
So it's just e to the it, isn't it?
Yeah, what does e to the it look like as t changes? What does it map out in the plane?
The normal circle.
The unit circle. So that's a unit circle. If I multiply by r, now I've got a circle of radius.
No.
It is intense. It's intense. It's great. That's great. So this circle here of radius r looks like this. As t runs from 0 to 2 pi, I run all the way around. How could I trace just half the circle? How could I trace just the upper half with this parameterization? What do I do to t?
Cut it in half.
Cut it in half, so I could just let t run from 0 to pi.
Yeah.
And then that would just be the upper half. What if I wanted the lower half? pi to 2 pi, beautiful. And so we can actually set this range to select pieces of the circle. What does this one look like? Yep, up right up here, right? Just this little piece right up there. Yeah, beautiful. So I'm gonna take that circle and just shift it by z naught. So it's z naught plus re to the it. Just moves everything. You're just adding z naught. It's just a translation of this circle. Just like vectors. When you add vectors, it's a translation. And then over here, let's just put theta naught less than t less than theta 1 to remind us t is actually an angle. And by choosing these two, let's make a neat little piece here. So make it just a segment of it. This is theta 1, theta 0, and this is theta 1, the angle. And we're sweeping just that little piece out. That's it. So now, you can draw all sorts of lines. You can draw circles. And I want to do one last thing. I got like 2 minutes to put this together. So let me show you how I would do this ice cream cone that I was doing during the meeting. So what if I asked you to parameterize straight line to 1 plus I, straight line to minus 1 plus I, and then a semicircle right on top of radius, what? What's the radius of that circle? Radius 1. Diameter 2.
Oh,
Yeah.
yeah?
Make sense?
Hold on, I was looking at the hypotenuse.
Yeah, no. So this circle up here, this is just the top. Oh, wait, you're right, Labina. If that's actually a circle where these are radii, I guess I was thinking
The semicircle up there.
this semicircle here,
Yeah.
that's kind of like that. Yeah, let's make it that one. Yeah. So you were thinking of the one centered here.
Yeah.
I'm thinking of the one centered right here. So this is circle of radius 1, centered at I. And let's say that I'm going to traverse it in this direction. Nice, straightforward orientation. Hey, challenge problem. You can do, here's a good to know. We got to end class. Find me the parameterization of that, please. You're going to want to use a piecewise definition. And you have all the tools. So you're going to describe this piece 1, piece 2, and piece 3. Piece 1, piece 2, and piece 3.
Beautiful.
Yeah. And we'll talk about that on Monday, or if you want to talk sooner. Oh, Friday I will, if you want to meet, I'm going to be working from home, so I'll have to Zoom with you, but I'll gladly Zoom. Just let me know. We will Zoom together. Sound okay? Thanks, friends. I always appreciate you deeply, and I always look very forward to being here with you.